In this lecture, we're going to start to finish up the SN2 reaction by looking at some of the kinetic details. So this is moving away from predicting products and directly proposing like curly arrow mechanisms to thinking more deeply about what's actually how this reaction is working from more of a physical level, I guess. Yeah, so like thinking about the physics and that sort of thing with regard to the SN2 reaction. Okay, so getting into it, let's start with just let's show the mechanism again one more time. So let's do a mechanism practice, and we're going to use a very simple example. Let's have NaOH adding to CH3Br. And I know we've talked about this. I know we've shown that you can cross out the Na and add to the carbon atom, which is a delta plus being directly attached to bromine with a delta minus. We add along the same trajectory as the carbon-bromine bond to push it off through backside attack, inversion of the tetrahedron, and if it was chiral, we would have inversion of configuration. Okay, we've talked about all this stuff. I know, but it's helpful to bring up again as we look at the details of the reactions from a kinetics and thermodynamics perspective. What I first want to point out is that this idea of a concerted reaction. The SN2 reaction is a concerted reaction. Okay, and what this means is that bond breaking slash bond forming events happen simultaneously. They happen simultaneously or, quote, in concert with each other. So happen simultaneously or in concert with each other. And now the big thing about concerted reactions is that, so concerted reaction, so maybe this, I should have drawn an arrow from concerted reaction. I mean, it's true of SN2 reaction also, but the definition of concerted reactions are that bond breaking and bond forming events happen simultaneously. They happen in concert with each other. Another way to think about this is that concerted reactions do not have intermediates. So concerted reactions do not have intermediates. Now, with that in mind, let's consider the energy diagram for the SN2 reaction. So the energy diagram for the SN2 reaction, so if you recall, we have free energy along the y-axis, and we have reaction coordinate along the x-axis. So if we've got starting materials, and this is going to be mostly our haloalkane and the nucleophile, when we do a reaction, we generally have an exothermic process in general with SN2 reactions. So this is going to be the product plus our salt byproduct. Now, to get from the starting material to the product, we have to proceed through a transition state, and that will get us down to the product. So right here, this atop the hill is our transition state. Now, this is the entirety of the energy diagram. Okay, there are no intermediates. If there are no intermediates, there's only one transition state. And that transition state, if you recall, is where the nucleophile is adding to the carbon atom, which is then losing the X group, and it's a trigonal bipyramidal geometry. So you've got a line going down, a wedge, and a dash. And maybe you could have like dots to show that the bonds are half formed and half broken. But that's our transition state geometry. And so this is an example where we have a nice simple energy diagram, starting materials, transition state, and products. In addition, we have, we're able to actually draw the geometry of the transition state. So with this in mind, we can actually, with all of this information, we can actually start to think more deeply about the reaction. And in particular, I want to think about the kinetics of the SN2 reaction. So let's start to build the, what I want to do is build the rate law for the SN2 reaction. So the kinetics of the SN2 reaction, it's a nice discussion because what we want to do is answer the question, what thing or things control the rate of the reaction? Okay. And I want to know that because I want to be able to know how fast will the reaction proceed. Okay. Now to answer the question, how fast will a reaction proceed, we need to derive the rate law. Derive has such a strong mathematical connotation. Let's just put determine the rate law. So we're not going to be doing some high-level calculus here. We could. It'd be fun, actually, and I mean that. Makes the calculus exciting, which is nice because sometimes you learn calculus and you don't know why you're learning it. Okay, so what turns out is that the rate is determined by several characteristics of the reaction. So the rate is sort of influenced by several attributes in the reaction: temperature, pressure, moisture, yeah, things like that. You set up an experiment in the lab. What are some things surrounding you that could influence the reaction? We could have even lighting, for example, could influence the rate of the reaction. So a bunch of things can control how fast or slow a reaction proceeds. But one thing to think about is if we're doing the reaction in a controlled laboratory, reasonably controlled, even in an old building like Farr Hall, we can hold a lot of this stuff constant. So let's hold all of this constant, and we're going to put that into a number that we'll label with a little k. So this is a little k. Let me write lowercase k. And little k is our rate constant. It's some number. That number changes depending on what type of experiment that you're doing. So it's not important what the number is. Let's just recognize that there are so many things that can influence how fast or slow a reaction proceeds. A lot of those things we can actually hold constant. They just won't change. Like if I set up an experiment open to air in a fume hood in Farr Hall, the temperature and pressure is not going to change dramatically each day. It shouldn't anyway. Okay, so we're going to hold a lot of this stuff constant. So what do we want to vary or pay attention to? What variables do we want to study? And in general, it's the concentration of what goes into the reaction. Concentration of what goes into the reaction. In particular, it's the reactants. Okay, this is very useful because the concentration of the reactants is proportional to how much reactants we are adding and mixing into the reaction. It turns out that if we understand how the concentration of the reactants, how changing them influences how fast or slow the reaction is, we can get a lot of insight into what the mechanism for the reaction is. So let's look at that in more detail. So the concentration of reactants is written like this. We put brackets around the reactant name or the reactant structure, and that tells us that we're talking about a concentration of the reactants. Now, the reason why we like concentration as opposed to mass or volume, like if I want to know how much I'm adding to a reaction, shouldn't I just like write down the mass, right? Or the number of moles? Well, concentration is an intensive property. Concentration is typically mass or moles over volume. So mass over volume is density, and moles, mass over volume is density, recall. Moles over volume of reaction, that's equal to concentration. Okay, density is fixed for a particular substance, like at a certain temperature. So the temperature of, the density of water at standard temperature and pressure and all that stuff is 1 gram per liter, milliliter, 1 gram per milliliter, sorry. But what we can do in a reaction is add solvent. And if we add a bunch of solvent, we increase the volume of the reaction, even though we haven't changed the amount of stuff that we've added in. So that's where concentration and volume differ, concentration and density differ. In density, the volume is the volume of the stuff that we took a mass of. So it's fixed based on the amount of, so if you add, whatever. With concentration though, we can change the concentration by adding more solvent, but still like it's an intensive property, because if we have a 1 mole per liter of some solution and we add 5 liters of that versus 2 liters of that, the concentration is an intensive property. It doesn't matter how much stuff we've added with that particular concentration, the concentration is not going to change. Okay, now with that said, we're going to rely on concentration as our attribute to study as we're understanding reactions. So concentration, maybe I made the discussion of concentration more complicated, but anyway, that's what we're going to use. So the reactant concentration could be 1m, for example, and the m stands for molarity, or moles per liter, and the volume in this case is the reaction volume, not the volume of however many moles of stuff that we added. Or we could have the concentration be in grams per milliliter, where here, even though this looks the same as density, this is the reaction volume, milliliters. Okay, anyway, so we have these concentrations that we could use. What this means, at the end of the day, stepping back from what a concentration actually is, maybe I made that more confusing, rate is equal to some K times the concentration of the reactants. Okay, that's it. The rate of the reaction, based on how we've defined K, the rate constant, is only influenced by the concentration of the reactants. If you increase the concentration of the reactants, K times a bigger number is a bigger number. You then increase the rate of the reaction, okay? And so some ways that you could increase the rate of the reactants is more reactants or less reaction volume. So you could add more of one of your reactants, or you could add less solvent, which is used to determine the overall concentration of the reactants, because solvent will just kind of increase the volume and thereby decreasing the concentration of everything. Well, here's the kicker. Okay, not worrying about the numbers directly, like whether it's a 1 molar or a 2 molar solution. The kicker is that the we can only, or let's write it this way. Rate is only affected by reactant concentration, and I'll put that in brackets so you know that it's concentration, for reactants involved in the rate determining step. So that's a really important idea. As we're discovering and elucidating rate laws, the only things that we can include in brackets and multiply by K are those things that are involved in the rate determining step. Anything that's not part of the rate determining step does not influence the overall rate of the reaction. And so we can't include them in the rate law. It's just the rate determining step. So it's just those reactants that are involved in the rate determining step. Now, I'm going to ask us a question before I turn pages in the notes. What is the rate determining step? Maybe I'll just do this on the next page notes. That makes sense. I took a second to pause. We're all caught up. Okay. So this leads me to ask, what is the rate determining step for the SN2 reaction? So what is it? What's the rate determining step? Well, hang on a second. Willoughby, there's only one step, the conversion of starting materials to products. A second step would be like if we went starting materials to intermediate to products. That would be a two-step process. We have no intermediates. There is only one step. It's a concerted reaction. Because it's a concerted reaction, that tells us right away there are no intermediates. If there are no intermediates, that tells us that there's only one step. Wonderful. Okay, so we have just one step. Now what this means is that if we only have one step, then really the reactants that we put into the reaction, they're all going to influence the reaction. So the rate is going to be equal to K times the concentration of all reactants. Well, what are the reactants? They are the electrophile and the nucleophile and the solvent. Wait, not the solvent. The solvent does not participate in bond breaking and forming reactions. I'm going to cross that out, less so. Okay. It's not involved in bond breaking or forming reactions. It's not really a reactant. It's just a facilitator. It really, now that we can look at it this way, it helps to dilute the reaction so that we're at appropriate concentrations, okay? So it helps to decrease the concentration of certain reactants so that the reaction is a little bit more under control. Okay, now what this means then for the rate law is the true rate law for, the rate law is just rate equals some reaction rate constant K times the concentration of some stuff. So rate law for the SN2 reaction. And I need to do a better job of making sure that my K is a little k. There, emphasize. So it's going to be K times the nucleophile times the electrophile K times the nucleophile times the electrophile, both as concentrations. So this is concentration of nuke times concentration of haloalkane. So X is times concentration of haloalkane is the concentration of our electrophile. Okay, so with this rate law, we can now ask interesting questions about the reaction related to kinetics. We could say, what is the overall order of the SN2 reaction? Well, the order, this is the sum of the concentrations exponents. The sum of the concentrations exponents. Well, there aren't any exponents. Rate equals K times the concentration of nuke. There's no exponent though. Well, there is. There is an exponent there. That exponent is 1 multiplied by the concentration of the electrophile. There's no exponent there. Well, there is. It's 1 because anything to the first power is just itself. If there were truly no exponents like 0, then the number would be 1, and that's not accurate. The concentration can change based on how much solvent or stuff that we add. Okay. So if we take 1 plus 1, that's equal to 2. So the overall order for the reaction is 2. Sometimes we like to call this a bimolecular reaction. It's got the concentration of 2 things in its rate determining step. Okay, and the exponent thing is helpful because sometimes in some chemical reactions, completely unrelated to this, we could have a rate constant times the concentration of something twice. So maybe it's A plus A gives product B. If A plus A gives product B, and A and A are both involved in the rate determining step, then it's A times A, or A squared. So 2 is the exponent. We just take 2 plus nothing, which is equal to 2. That's also a bimolecular reaction, which is different from a unimolecular reaction we'll talk about next time, where the exponents all add up to 1. Most importantly, for this, I wanted to give us some context as to where the 2 comes from in the name for the SN2 reaction. Okay, so in this lecture, we did a deep kinetic analysis of the SN2 reaction. We're going to use this information and analysis approach going forward to try to better understand some other related reactions of haloalkanes, starting next lecture with what's called the E2 reaction. So